Hello everyone. So we're going to analyze this beam, and this is going to be through the method of slope deflection. And here's the beam. As you can see, it has a uniformly distributed load of 18 kilonewtons per meter, and as you can see, all the distances are 5 meters. So this is the question. The first step to analyzing this beam is finding the fixed end moments. Since that we have a beam that has a uniformly distributed load, which is a UDL, and a span of 15, and each section has 5 centimeters, so it's easier to work with it compared to these other beams, which may be having a uniformly distributed load and maybe a point load, or you just know all of that, right? So the first step here is finding the fixed end moments, where we're going to first work with a span AB. And when we're finding the spans of AB, since it's a uniformly distributed load acting on a span, we're going to use the formula W L squared over 12. This one works for a UDL. So when you're calculating for span AB, it's the 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 moments for MFAB, it's going to be a negative. Meanwhile, the other, because it acts in a clockwise direction, and this one acts in an anti-clockwise direction. So the same, where I found 37.5 kilonewtons meter, it's going to be the same throughout the whole load, the whole beam, I mean, because it's a uniformly distributed load across a uniform length, which is 5 for each span. After you've calculated the fixed end moments, we're going to calculate the slope deflection equations. But since we had the far fixed end being a fixed end, not a roller or a pin, the angle at A is going to be a 0. And that's the reason why I have it as 0, and I've used the theta B has remained the way it is. And you're going to calculate the same for all these other parts. And also remember, theta D is going to be a 0 because the far end is a fixed end, not a roller or a pin. After you've calculated the slope deflection equations, we're going to calculate the equilibrium equations, where the joints, we have a joint B and a joint D. But since this is a UDL, let's first work with one joint. The joint we're working with is joint B, which has two sections, BA and BC. When you equate all the values, it's going to give you this equation. But remember, the load was uniformly distributed. If the load is uniformly distributed and theta A and theta D were already 0, theta B and theta C are equal. For which I decided to take it as theta B, and I substituted it there, and it gave me the value 0. So when you substitute in all the 0 values into you feed them back into the main equations that we found, the values are going to remain like this. But then after you found those values, you're going to have to calculate the support reactions. And when you calculate the support reactions, I first did it with the first span, which is AB, and that's by taking the moments about A in the anti-clockwise direction. I found error B1. Remember, this is now I'm using sectioning, because you can use inspection, but I think it depends on how good you are with it. Though I prefer to use sectioning to do the beams, and that's the reason why I have the RB1. And then I'm also taking the vertical forces. You're going to find 45 for RA, for the reaction at A, I mean. And you do the same for all the spans, but you make sure you're going to calculate the total B and the total C, which you can see the total B, I have it as 90, and the total C, the total C is also 90. After that, you have to calculate the shear force values, and this I have started it by calculating the shear force at A, which is 45 kilonewtons. No, write it here. I didn't write it, but I forgot. It's supposed to be there. And then the moments before right after A, it's 45, and left of A, it's a 0. You calculate the shear force values. After calculating the shear force values, then you're going to plot the shear force diagram, which is more of like, it has a uniform frequency movement, as you can see it here. Then we calculate the free moment diagram values, but by calculating the moments. And since it was a UDL, you're going to calculate W times L squared over 8. That is the formula for UDL moment. And when you calculate it, all of it gives you 56.25. And then you draw the free moment diagram. Then the end moment diagram. Since the values that we had were 37.5, which is literally a uniform value, it's going to give you a rectangle. Don't forget to write the signs. Then we will also find the final bending moment diagram. When you plot this against this, then you shade the parts that are above this. And every value that is below the end moment diagram is a negative, and every value that is above it is a positive. So that's how the number is. Bye. And please don't forget to like, subscribe, share to follow more structure analysis numbers from me.